total potential energy of bar subject to load is given by, first we have to discretize the total element. Here is n number of elements are considered. So the bar has been divided into number of elements, and then finite element we apply the equation. So in this is the equation governing the equation of motion of this particular bar element. So here n is varies from 1 to n, means n number of elements. The total potential energy is equal to its strain energy equation. This one already we know that strain energy of integral volumetric stress into strain into its volume. So similarly strain energy into its total forces, the forces. Here we consider in the finite element method there are three types of forces. One is body force, this one is body force, particularly this one is body force, means n number of elements. Suppose one element we consider body force into its displacement vector into its volume. So another force is surface or traction force. This one, this represents the surface and traction force. Another force is point load, like it acts in a small point. That point load, P is the point load, U is the its displacement. So from this equation we will have to derive the element stiffness matrix and its force vectors by using this finite element approach. So first we will derive the element stiffness matrix by using its strain energy in terms of U. So we know that U, this one is strain energy, is equal to U half into integral stress into strain into dx, and this equation 5 represents its strain energy. From this, with the concept of strain energy, we can easily derive its element stiffness matrix. So we know the stress strain relationships previously in the mechanics of solids. Our previous classes already will discuss. Stress strain is equal to change in length by original length dou u by dou x, and stress is equal to E into its strain. From the Hooke's law we can say that this relations we know. So we can approximate the axial displacement. So we know this equation, U is equal to n1 u1 plus n2 u2. So n1 and 2 are the shape functions of this bar element, u1 u2 are the displacements at node 1 and node 2. These things we know that. So with this n1 and n2 are also we derived when the shape functions concept. N1 is equal to 1 minus x by L, N2 is equal to x by L. N1 and N2 are the shape functions of this two noded bar element. So we have to substitute this strain is equal to dou u by dou x. So strain is equal to dou n1 by dou x, dou n2 by dou x, dou u1 u2. In the matrix form, vector form, you represented in equation 9. So from this simplifying, already n1 means we know the differentiation once, so we will get the minus 1 by L, u1 u2. So we can rearrange. Finally we will simply form it. Strain is equal to B into U. Here this B is the relationship between the strain and its displacement relation matrix. So this is important for deriving this stiffness matrix. So this one is B. Already we derived here about equation. So stress is equal to, we know equation Young's modulus into strains. Young's modulus means here we can remodify into its matrix form or vectors represented. Stress is equal to D to B into U. Here what is this one is stress. Sigma is stress. D is material property matrix. B is the relationship between the strain and displacement matrix. U is displacements. These are the terminologies in equation 10. So D is E. Here is E because it is a one-dimensional element. Simply we can say that it is a Young's modulus. We know that strain energy half integral stress into strain AdX. We need to substitute this just for in terms of its vector representation. Just sigma stress transpose into strain into dx. So we need to substitute these values. Already we know this stress is equal to this one, d into b into u, and strain is equal to d into b. This we know these things. So we need to substitute in strain energy equation, and we will form like this: a into half u transpose b into b transpose b into u. This one is the stiffness matrix of this bar element. So this is the equation represents strain energy in terms of its matrix. So we need to integrate this one and substitute its magnitude. Its varies from 0 to, this is a non-dimensional element, its length is varies from 0 to L. So directly we can substitute and integrate. Finally we can calculate. This one is the strain energy is equal to u of u transpose this matrix into u. This matrix represents element stiffness matrix. This matrix is known as element stiffness matrix. So this element stiffness matrix is used to solve the solutions of this bars. So element force vectors. So in the potential energy concept, there are two parts. One is strain energy, another one is force vectors. So force vectors we will calculate one by one. Body force vector. Body force is equal to Fn. Body force represents this one. It's body force u into dv. So this one is once again in terms of its matrix transpose, we form it like this. And then we know this u transpose, n1 u1 n2 u2 transpose body force. This one is body force into area into its dx. So substitute this n1 n2 and its separate the matrices and vector like n1 n2 and u1 u2. Rearrange this equation. Finally substitute its n1 n2 values, known values, and finally we'll get these equations. After substituting these boundary conditions, we will derive this equation is body force vector of this bar element. So next, traction force. With traction force matrix, we know this equation, and the starting equation represents all the body forces, like all the forces like body force, traction force, and point loads. This one is traction force. So traction force Ft is equal to Tf into u into ds. So in this transpose u transpose into t into t suffix x and dx. Then substitute this t u displacement equation in this and separate the matrices like n1 n2 transpose and u1 u2 transpose. And finally we need to substitute this shape function values and integrate. Finally we will find the traction force is equal to this matrix because it is two noded element. So similarly, finally k q is equal to f. This is the governing equation of this finite element method. So in this u strain energy equation, this one, the total potential energy is equal to sum of its internal energy and its body forces. So we need to substitute these equations. Substitute. Already we derived its stiffness matrix, force vectors, and point loads. So substitute in this equation. Finally apply the minimum potential energy approach because it is easy to solve and easy to understand. So apply the minimum potential energy approach. Finally we'll kq is equal to f. Finally we'll conduct the k. What is k here? K suffix a is element stiffness matrix of this particular two noded bar element. U means displacement vector, f means force vector. It is force vector means it's combination of body force, traction force, and point loaded. Whatever the forces are there, we need to consider on the force. According to that we will consider. This is the force vector. So in this class what we learn, Strain displacement relations with there. This is strain is equal to B matrix into U displacement vector. What is B? B is very important here. B is the relationship between the strain and displacement matrix. On stress strain relations also we derive. Stress is equal to its Young's modulus into B into U. So B is this one, minus 1 by L, 1 by L vector. And element stiffness matrix also we derive. The element stiffness matrix of this two noded bar element is K suffix E is equal to AE by L, 1, minus 1, minus 1, 1. And the force vectors due to its body force. This is the force vector due to body force of LAB, A by 2. And another one is element force vector due to traction force. And this one. This is the KQ is equal to F by applying minimum potential energy approach. Thank you.